Okay. Can you hear me, guys? So today's the day when HDMI fails me, surprisingly, after reliably working for us for the last how long? For the last months. Did anyone have a class here before this one? You had?
I had one yesterday.
It wasn't working yesterday. You should have told me earlier. Do you have a suggestion? Oh, so someone set up a projector. Okay, and that's HDMI. Okay, got it. Nature. Okay, that's news. Yeah. Got it. Thank you so much for this one. I was thinking, yeah, you guys should have told me like right away. You think I? No. I have no idea what's going on. Like it's it was working on Monday for us, right? Yeah. Okay. That's a surprise. So what do I do here? I just. You think it's on? It looks like it's on, right? Then I will switch this file. Again? Apparently, yeah. It looks like that's why someone did a setup. We're lucky that it's already there. To boot for us. Come on. Okay, let me try this one. This HDMI cable, maybe this one will work. Oh, this one works better. Just quickly figure out how we can use it. So I guess this is the best we can do today, and hopefully it will get fixed. So I understand that the picture is small. Well, apologize for that, but apparently they had a technical issue here between Monday and today, and let's just try to. If you can't see something, but I believe that my slides should be visible on this screen. Now let me just on the lights. And people on Zoom, I assume can hear me well, right? And people in the class as well. Okay, so today, what we're going to talk today about is representation of real numbers and operations on real numbers on the machine. So up until now, what we were doing is the following. We always talked about integer numbers, right? And that's okay, right? So that's unless you're doing a lot of numerical computations, like today the most popular related to artificial intelligence, but back in the past it was like weather prediction and stuff like that. Most of your life outside of the class will be spent doing operations on integers. Like as a systems developer, I haven't seen a floating number in a while. However, it's not true for every domain, right? As I said, there are domains which require computations on real numbers. You might be working for NASA lab, national lab, or something like that. And if I ask you a question, if you have a real number, something like 3.2 in a decimal, how would you think you can represent this number in the machine? So what you're suggesting is to say, let's imagine we have, okay, so, let's imagine we have two integers. Oh, sorry, like misalignment. Let me erase everything real quick. Misalignment of my hand on the drawing pad. You can say I will have two integers, and if I had a number 3.2, I will put 3 here, and 0.2. How will you represent 0.2? Just a 2, like this. Then how will you represent number 2.5?
well, then 25 seems to be larger than 2, right? So you're running into a weird problem here. You used to have what?
Use a ratio of meters to represent the flow.
That's a great idea. You can say, look, what if I say that this 325 will be represented as either a ratio, something like 325 divided by, let's say, 100, right? Agree? Then you can say, well, I don't even have to keep this 100. I can agree on the fact that all my numbers are divided by 100, right? And then you can just say, let's use a 32-bit register and just put 325 here and do operations on these numbers. But the moment you want to put it on a screen or something, you saw that the real value of this number is not 325, but 325 divided by 100, right? And this representation has its advantages, right? So it's a fixed point representation, and it's actually was used in practice. I haven't seen it frequently used recently, but it was. Why? Because operations on those numbers are as fast as operations on integers, right? Because we know that addition has 1 cycle, multiplication has 4 to 5 cycles. Remember this logarithmic stacking of adders, right? Which allows us to build a fast multiplication. And we looked at the tables on modern x86 hardware, and division is what was roughly, I think, 15 cycles, right? So that's not bad, but there are some disadvantages to this representation. Let me take the question here.
Try estimating the decimal using a binary, like decimal source, for example, like 3.5 would be like 1, 1.1.
Say again.
We are representing like the decimal in terms of binary. The decimal.
Oh, no. When I keep going through those examples, I implicitly assume that internally numbers will be represented as binary. It just for simplicity of, since we're used to speak in terms of decimal, right? It's easier for us to kind of quickly eyeball those numbers, right? Everything is binary. Although historically there were machines which were building hardware for operating on decimal numbers as well. So you kind of, and it's in the book, so I recommend you to read it, and it's fun to hear the argument about it. But if we adopt this representation, which you suggested, this one, what do you think is the major disadvantage of this one? Although it definitely can, it's a viable choice. It's not like, let me take you biggest.
We can only reach a certain level of precision, only divided by 100,000.
Exactly. So what you're saying is that in this representation, numbers which are in the neighborhood of 100, right? So like above up to like 2 to the point, since we like we took away a couple of digits of precision, at least in decimal, right? But imagine in decimal we can hold. It's a little bit of a weird example, but imagine this register could initially was able to hold 10 decimal digits, right? And we took away 2 at least, right? So we can represent 4 to keep something after the point, right? And here instead of 10 we will have 8, right? So we sacrifice some precision, but in this neighborhood everything is fine, right? You can keep adding and dividing numbers. But what will go wrong is, imagine you have a number and maybe it's some of your calculation which is something 0.00, a couple of zeros here, and then 38, right? And you say, look, this number is in my representation, it will be rounded to 0, right? So I lost all information about this number. That's not good, right? But maybe, and suddenly, you know, your computation keeps adding those numbers, and imagine you have kind of like 6 decimal digits here, and like, which means that if you keep adding 1 million times, you eventually reach 1 here, right? If you keep adding for like if you do that in a loop which has million iterations internally and maybe million iterations externally, right? So it's a million by a million. Then obviously you start your number is growing, and then you have a ton of ones or like some other digits before the dot, right? So which means that your numbers can move around in the neighborhood around 0 and from minus infinity to plus infinity, right? Agree with this? So we started somewhere very, very close to 0 here with the 0.00 ... 38, and we were increasing this number, and eventually we got somewhere over here, right, in the order of millions, right? And ideally, we would like a representation which would allow us to represent in a flexible manner, represent any number, any real number. And when I say any, it's a stretch, obviously. The hardware will have limits, but at least have some meaningful way to talk about numbers which are close to 0. And if your computation evolves, which go into like orders of millions or billions, right? So if I ask you, how would we build this representation? What would you guess?
Well, like, it seems like you want something like scientific notation where you have like some amount of accuracy, so like 3 decimal points times 10 to like the X number, because then you can store like this part accurately, and then also like how far to the right or left it is.
Right, and that's exactly the idea, which is called a floating point, meaning that you will have 2 parts of the number. And as you say, it's a scientific notation. So for example, this number will be represented as 3.8 multiplied by 10. And how many zeros are here with some power, let's say -5, right? And if you have, it's a very small number because this negative of a negative power, it's essentially dividing the 10 to 5 times, right? And if you have a large number, you will put something like 3.8 multiplied by 10 in a power 6. So it will be like 3.8 millions, right? And this allows you to, in one setting, in one representation, you can represent both very small numbers close to 0 and large numbers close to like, which depending on how many bits you designate for keeping those digits, right? Going towards infinity this way, and of course this way, because you would like to represent negative numbers as well, right? So, and this is what is called a floating number. So this standard was introduced by IEEE in 1985. There was a revision to this standard, but essentially today it's this is the most universally adopted standard for representing floating point numbers or real numbers. So there are two representations. One is called single precision, or something in a C language, you will write something like a float, and C++ as well, or double precision, which essentially instead of 32 bits, will take a 64 bits, and this is called a double. And just to give you a little bit more details about what this number is, as you say, we will think of numbers as represented in this normalized scientific notation, which means that there will be only a single non-zero digit, like here, 3, to the left of the decimal binary point, right? And then it will be some number of digits here and multiplied by an exponent. So, right, for example, if you do that in a binary notation, and you have obviously this, now instead of like all the possibilities 1, 2, 3, 4, 5, 6, 7, 8, and 9, your only possibility here is always 1, right? Can you actually see it from there? I'm sorry. And you have a bunch of digits here after the point. And what it means really that you have 1 plus this 0 multiplied by 2 power minus 1, which is 1 second, right? Then this 1 multiplied by 2 in the power minus 2, which is 1/4, and so on. And here 1 to this 1 multiplied by 2 power minus 6, right? And whatever this, if you add all this, right, power, so it's like 1 plus 1/4 plus 1/8, 1/16, 1/32, 1/64, right? You get a number, and then you multiply it by 2 in a power minus 5. And of course, -5 will also be represented in a binary form. But again, for simplicity of polite reasoning, right now I will use the decimal number there, right? So if your number is not normalized, something like you have, again, let me use a decimal number, 38.56, right? You first have to normalize it and say it's a 3.856 multiplied by 10, oh, sorry, by 10.1, right? Which means that that's your normalized representation, but in practice, you multiply by 10, so you will get 38.56. But you keep all of these things in binary, and I will just go over the details how it's done. So any questions about why it makes sense? And we'll go and we'll figure out the details of how it actually is saved in memory of the machine and stuff like that, and we will take a look at the iterations which machine can do on those numbers. Good. So this is believable. So this is the actual representation. And again, so remember I said there will be two. There will be a single and double precision floating point numbers. And this is a single precision. So the total length of it is still 32 bits. The highest bit represents the sign, right? So the number can be positive and negative. We have an exponent, which represents this power, right? Which, and it's not like, this is a slightly simplified notation, and I will go into the details and explain how it's actually interpreted by the machine, but at a high level, it's exponent tells you the power of 2 by which you have to multiply this number. And then the fraction, which essentially the number itself, right? So how you interpret the number at a high level is you take the sign bit, raise the -1 in the power of s, right? And if it's a 0, then it's a positive number because any number in the power of 0 is 1. If it's a 1, then it will become a negative number. And then you take a fraction and multiply by the 2 to the power of exponent, right? At a high level, do you get the idea how what it means? And if I ask you a question, why do you think we made this split? First of all, we decided that we will have 8 bits for the exponent, 23 bits for the fraction, and 1 bit for the sign. So in the past, we were using a two's complement, right, to represent negative numbers, right? In this notation, the design choice was made to keep the sign bits separate, right? And it simplifies and accelerates comparisons, so it accelerates sort algorithms on those floating numbers. But why do you think it's a meaningful choice to take 8 bits for the exponent and 23 bits for the fraction? Or what would be the trade-off? What if we like split it roughly in half, like 15 and 14, for example?
Depending on which way you go, you can either have a higher range or more precision.
Right. So if you're essentially saying that we will, like maybe to reason about, let's just first understand what is the maximum number which you can represent in this as a double, as a single value, as a single floating point value, single precision floating point value. So let me just make a couple of observations which are kind of important here. So remember that we always said that this digit on the left side of the door is always 1, right? Do you agree with this? In a normalized form. Because it's a binary system. In decimal, it would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But not 0. But in binary, it's just 1, always 1. Which we can do the same trick as we've done for those relative branch instructions and jump instructions. We say, look, we don't have to really keep this bit around. If we know that it's 1, let's just know it and don't bother even about it, right? So, and in practice, what is done is that it's always this form, 1 plus the fraction. So those bits of the fraction are actually added to 1, which we implicitly assume that it's always stored there, right? So, and if we know that, and we say, okay, like what will be the largest number which we can represent, right? So our fraction, which is, imagine it's all ones here, right? All 23 bits, right? You know how the numbers work. So it's 1 second plus 1/4 plus 1/8 plus 1/16, right? Plus 1/32. It's all the powers of 2 up to this max power. Agree? What will be this sum? I mean, or approximately what this sum is trying to reach. If we will continue adding those numbers. Yeah, it reaches 1, right? It's gradually getting towards the 1. So if we eyeball this number, so this sum is almost 1 plus the fraction, right? So because remember that we always say 1 plus fraction, and this is called a significand, right? That's another name which is used here. And so this is close to 2. And then you say like it's 2 to the power all bits of the exponent here, and it's 8 bits. And now let's ask a question. So how many numbers we can represent with 8 bits? 256, and it's logical to say that you represent numbers powers from 0 to 255, but
Also, I have a question about the exponent. It's not be negative, or it's also be positive, right?
exponent has to be negative, right? Because you really need to represent numbers which are close to 0, right? So, and this is where we're getting. So this exponent, the sign bit is a sign bit of the number. But the exponent, we can either say that it's represent powers from 0 to 256, but as you said, like we really need negative exponents, right? Because we need numbers close to 0, right? So that's why here we actually represent numbers which are exponents from, like they say here, from negative 127 to positive 127. No, 28, right? And so essentially we kind of shift it. We say, okay, this is the range which we can represent, but really 0 will mean 0 minus 127. So it's an exponent which is negative 127. And if this exponent is really 127, then it's really 0, right? Because you are subtracting 127. Okay, got it? So then the maximum number is this 2, which is 1 plus fraction, right? So which is plus to the 2 to the power 128. And this is the number which is in decimal form equals to this 2 to the 10 to the power 38. So it's a relatively large number. It depends on, again, your domain in which you're doing the computations. So it may not be large enough for you, but it's large enough. Correct. So what you're talking about is there might be 2 overflow conditions. First, the number is too large and it just doesn't fit, or number is too small and it's called an underflow. So it's an overflow and an underflow condition. And it's absolutely like, and of course you can understand that there are gaps, right? Because between any 2 integer numbers, there will be an infinite number of real numbers, right? And you can't represent them all because you only have so many bits in a fraction, right? And I'll take a question in a second, but really what you're talking about is that if you're sacrificing the bits of the exponent, right, then you're trading this power, which means that the range of the numbers which you can possibly represent shrinks a little, but the precision within, like, you can differentiate. If you have more bits in your fraction, you can represent numbers which are closer to each other, right? And they made this trade-off, saying that it's good enough for everyone, right? But of course, there will be scientific applications in which those numbers are not precise enough, and that's why they came up with another representation, which is called double precision, which just slightly increases the exponent from 8 bits to 11, because the range is apparently long enough for most use cases, because this is a huge power, right? So like I don't even know what it's called. I don't know if there is a human readable name for this power, right? So I go like like we know gigabyte, what's next? Terabyte, and then what? Petabyte, yeah. So up to peta, I guess I can count. I'm sure there are names for those numbers, but this is a huge range. So it doesn't make sense to extend the range by a lot, but the fraction will allow you to represent numbers more precisely, right? Because as we will see in a second, all these mathematical operations, addition, subtraction, multiplication, division, will, like, you will be running out of bits in a fraction, right? And then you will have to round the numbers, or just simply drop the bits, which is just truncating them. There was a question.
Is there no representation for a zero in floating point?
That's a great question. So what you're saying is that how do we represent zero, right? Because it's 1 plus a fraction. So what would be your guess? How can something? Wow, that they could have done the sacrifice, but they decided that zero is so precious that they cannot sacrifice zero.
Is this special representation?
Yeah, it's a special representation. But what do you think is the logical one? All zeros, exactly. That they say a special case. If everything is zero, and I have those special cases on the next slide. But if all the bits are zero, it's really zero. And it's nice because, you know, if you we'll go into the details how they represent very, very small numbers, but no matter how small you pick, if you do enough operations, maybe if you keep adding for a month or for a year, right, you will still get away from zero and the number will be growing. And it's a real problem. So those computations, they diverge sometimes, you know, you would assume that, you know, you're computing something correctly, but no, it diverges and you're computing something what doesn't make sense anymore. Okay, so are we good right now on this basic representation of the number? We got the idea, right? So, but it allows you to represent numbers which are close to zero and far away from zero with some sacrifices. So, okay, so a little bit of details, right? So the number 0 is a special case, and which means that all bits of the floating point are zeros, right? That's a special number here. So the largest exponent value, however, with the zero fraction. So if the fraction here, let me just erase everything here. If the fraction is all the zeros and the largest exponent here represents the number which is plus infinity or minus infinity, depending on the sign bit, right? And it's again, it's a trade-off. So whether it makes sense or not, but they say for the scientific computations, it makes sense to represent infinity. And maybe you keep it around and then, you know, you say the final answer is infinity. In some cases, it makes sense, right? Because you said, okay, maybe we reach that number. Although again, like I'm not an expert on like those numerical computations, and it gets really probably complicated, right? So there is another special number which is called not a number. It's, for example, a result of division by 0, right? Which I was explaining to you last time. Mathematically, it's undefined, right? Because at some point you say, well, the computation doesn't make sense anymore. But maybe you still want to compute, you know, like maybe you have an array of numbers and you say, let's compute something for each element of the input, and maybe some inputs will provide some meaningful results and some will be undefined as not a number. And instead of like immediately terminating computation with an exception, for example, you can keep around this not a number representation and then just output it to the user, and user says, okay, look, yeah, really your floating point computation produced something what is not a number. Maybe I have to increase precision, maybe I have to do something else, maybe I have to reconsider how I'm computing this. But the answer is not a number. And so the way to represent it is this: take the largest exponent value, and however, instead of putting all zeros in a fraction, just put something else. And it means that this number is not a number, right? And what it means is that your, what I wanted to show you, we already talked about the representation of this exponent. So it's a bias here, right? So the real value is whatever you put there. So if you want to represent 0, you have to put 127. And for a single precision, the bias itself in 127. So then your power here will be 127 minus 127 equals 0, right? So you shift it. And this is how your number range will look. Right? So you know how to represent positive infinity. It's all ones in the exponent field, right? And a fraction field is all zeros. So the value is not a number if you put all ones here and some bits here are not 0, right? So it's a special not a number value, which means actually that your highest value is 2 to the power 127, right? Then you have 2. That's your 0. So your smallest value is, smallest normalized value is roughly 2 to the power minus negative 126, right? Because it's in your what is it I'm trying to say here? Oh, because if you put 1 here and subtract 127, right? So you get to negative 126. So this is your exponent, right? And your fraction is why is your fraction smallest? It shouldn't be normalized number. If your fraction is all zeros, then it should be 1, I would assume. So maybe an error in the slides, but let me clarify it. 1 to the point 2 to the point to the power 126, right? However, you say, look, but if I'm losing all those numbers in the neighborhood of zeros, right? Because if in a normalized form, this is the smallest number I can represent, you still have a bunch of numbers which are close to 0, for which you don't have representation, right? And those guys came up with yet another exception for this representation. And they said, okay, look, we can also have denormalized numbers, which are essentially if your exponent is all zeros, right? And your fraction is, so essentially this allows you to treat to represent a number in the neighborhood of zeros, essentially, instead of like just essentially break normalization and allow you to treat this number as just use this as a power. So essentially, and then it becomes up to the power negative 149. Okay, so maybe I didn't explain it super clearly, but again, you can read in the book, and maybe I will bring up a slide next time to explain what is going on. And the same for the negative numbers with a negative sign, right? Okay, so roughly speaking, is this range clear to you? So there is a couple of exceptions. Like normally, people don't like those denormalized numbers in practice because they kind of always represent a little bit of a puzzle, and that's why I don't really know them myself, right? So normally all the computations which you will be doing will be in this range, right? And if your number falls under this range, that's an underflow. If you go above, that's an overflow.
So, like, does nobody care that we lose quite a few numbers to the
What you're saying is that, roughly speaking, anytime your computation either triggers an overflow or underflow, you're losing precision, right? And you're also losing a lot of precision by just simply like adding two numbers. For example, the numbers, because you're running out of bits in a fraction, right? Not even in the exponent. It matters a lot, and it matters a lot, especially for complex computations. And today there is a giant area of research which tries to study and build different analysis, kind of like static and dynamic analysis, saying whether your computation will stay an overflow or underflow, or will stay normal and will always produce a reasonable result. So, and there are people here at the University of Utah who are doing this research. So Ganesh and Zvonimir were the two researchers. Zvonimir were American. Ganesh does formal verification, which we're coming up with tools which allow you to reason about your computation and actually reasoning and trigger, like essentially provide you with a warning saying that maybe you're doing something which will produce a result which doesn't represent reality. So this is my, oh, I have a slide for this, the normal number. So essentially, if your exponent is all zeros, right, then you say that your hidden bit is 0. That's what I was trying to explain. And then it just hidden bit first plus fraction minus the bias, right? And essentially that's your denormalized number, which they allow you to have around. That's again like a slide which covers all these special cases, not a number, positive and negative, negative infinity. But let's just take a look at a couple of examples, because it's nice to kind of talk about it abstractly. But if I ask you to represent this number, which is in decimal, negative 0.75, what do we have to do? How do we go about representing it? Who can tell me? How do we start? We first of all, we have to convert it from decimal to binary, right? It's a little tricky. So, any ideas for how to do this?
Okay, so right now, negative 0.75 is base. If you
Mhm.
want to put it in binary, you could put it to base 2.
We can, but and that's okay. So, but so yeah. So how we will convert 0.75 in base 2? Let me give you a couple of examples. So, for example, we know what these numbers are, right? So we said that imagine it's 0 point and then some digits here. So this first digit is whatever it's 1 or 0 is 1 multiplied by, for example, 1, 2 plus 1 multiplied by 1, 4, right? And so on, right? And so one way to see this number 0.75 is to say, look, it's actually a number which can be represented as 1, 2 plus 1, 4, right? Because what is happening is that you say it's really 2 fourths plus 1 fourth equals 3 fourths, right? Or this is exactly if you want to normalize. So what is the 75? That's 75ths over 100, right? Sorry. So if we say we want to get to 100 here, so we multiply both parts by 25, right? And we get exactly to 75 by 100, right? So if I show you this computation, this is how the math works. So then what will be the binary representation of this number? Huh? 0.11, exactly. So because this one represents 1 here multiplied by 1, 2, this one represents 1 multiplied by 1, 4, right? So this number is really becoming in binary negative 0.11 in right in here, right? And so now what do we do next to represent it as a floating point, single precision number?
So the sign will be 1.
Sign is 1, right? Because our rule for the sign is -1 raised to the power of s, right? So what will be we need to normalize it, right? So we have to rewrite, let me just change the color here so we keep track of 2 stages of this computation. So if this is not a normalized form, because our normalized form will be negative 1.1, right? That's how we want to represent it, right? And since we did it, so we say we will multiply this number by 2 to the negative power 1, right? So, and your fraction then becomes, since it's always, we don't keep this one around, right? Your fraction become this one, and your exponent becomes -1 plus bias, right? And so bias for the single precision is 127. So -1 plus 127 is 126. So that's your exponent, right? And so if you look at the representation of this number in a single precision form, this is your sine, this is your exponent, and this is your fraction. Is that clear?
Is this the rule of complement? Is this two complement?
No, it looks like, but it's not. It's just shifted by a bias. And so bias is different because it's roughly like to take the number in the middle, right? Because we said we can represent from 0 to 255. But since we say we want to represent negative exponents as well, we're going to shift them by 127. And so your 0 will become in the middle, and your negative 127 becomes exponent like that. Okay, so what if we want to do a reverse computation, right? So what? If we have a floating point number in a single precision format, which looks like this, right? So again, we take the sine is S. You guys have a question? No, I mean, if there's, right, exactly. Because we in a binary format, in a decimal, it could be, this value can be anything from 1 to 9, right? But in a binary, it's either 0 or 1, but since we always normalize the number, so it's always 1, so we don't just keep it around. And that's why we say that the fraction is, this significant is always, the number is really is 1 plus the fraction, right? Multiplied by 2, and here this exponent plus the bias. Okay, so if we take another example, like converting the other way around, so sine bit is 1, right? So our fraction is this. Our exponent is this green one here, right? And so I mean, I don't know this, I don't know the conversions, right? But really what it does is if you, I mean, I like to use Python, right? So if you plug this number into Python, then you will get 129. And we can, I mean, we can double check. So it's 6 zeros. Let me just quickly do it for you. If I do binary 1 0 0 0 0 0 0 1, so luckily it's 129, right? So this is what, remember there was a question actually yesterday about the notation in the homework where I was using this B or 0B, right? So it stands for the binary. So if I do something like 0x, it stands for the hex number. So if I do this, it's 255 because it's a XFF is a 255 is 255 in decimal. I can use binary notation like to any binary number, right? And it will output me. And if I want to convert back, so I can do this hex function saying, okay, for example, what is hex representation of 15? What is 16, for example, right? So Python is a powerful tool. So I recommend you to start using it. Start using it as a powerful calculator for your homeworks, right? Is it clear how it works? Right. So just again, so if we have a slide was a lot of binary numbers, so just don't be shy and just verify them, right? And then your fraction itself is this, right? So it's 1 plus 0 1, which is here, right? And so what is it? It's since this is 1 second by 0, and this is 1 by 1/4, right? So we get, eventually we get 1/4 is 1/4 if we convert it to decimal rule 25/100, right? And so this is our number 1 plus dot 25 multiplied by 2 to the power, since this is our formula for how we represent the exponent. So we essentially said it's 128 minus the bias here. So it's turns out to be 2. And so we have that if this one multiplied by 4 will give us exactly -5. Is it good or too fast? It's a little unusual, right? Like when I was looking at it, I was also surprised that this fraction doesn't look like a number which you were expected to see. One would say, okay, my fraction was 1/1, right, or just 1 here, right? And that's meaningful. But if you have something like, the point is that this represent powers of 2, right? So it's essentially, if you have something like 1, 1, 1, so this is 0 multiplied by 1, 2 plus 1 multiplied by 1/4 plus 1 multiplied by 1/8, right? Okay, so how do you think the floating point addition should work? And the algorithm is here on the screen, but let's go through this example step by step. So there's a couple of things which we have to pay attention. So in general, addition will go similar to how we learn it in an elementary school. So if we have 2 numbers, right? So for example, this 9.99 to the power 10 in the first, and then 1.610 10 to the power -1. We first do this alignment, meaning that we shift the numbers to the with the smallest exponent. So essentially, both numbers are normalized, right? But it's easy for us to add numbers which are in this which have the same exponent. Why is that? Because the mathematics here is that you can put the exponent here, right? And if those are not the same, then you can't do this trick, and you can't simply do the addition under the brackets, right? So that's why you first say that, okay, let's arrive to the exponent which is the same, and it's okay. You can arrive I was thinking whether you can like arrive to 10 to the -1, but you probably cannot, because you need to have this number represented like this. Okay, so I have a question.
Is the alignment done by like a compiler or?
What do you think? No, first of all, let's take a look at how the algorithm works. And I'm using the decimal numbers just because it's easier for us as humans, right? Because the moment we switch to binary, it's just another order of complexity. And you say, okay, look, I have to like quickly understand what it even means, like, because when you have a number which is this, right, it's kind of natural to us. We understand that this is 110, this is 100, and this is 1,000, but with a binary, it quickly becomes tricky. So this alignment is done by the hardware. It's essentially because the hardware is designed to add any 2 floating point numbers which you have in memory or in registers, right? So the hardware obviously works on registers, but we first load them from memory into registers that do the addition. And it looks at the numbers, and it upfront doesn't know which numbers will be there, right? So maybe this exponents will be completely different, like maybe -127 plus +127, right? And then it has to do the addition on those. But if you do this, if you align these things, then you can simply do the addition, right? And it will be, if you do this 9.999 plus 0.016, 6 plus 9 is 5, 1 here, 1 here, 1 here, 0, 1 here. So that's your number, right? And am I right? Right, I'm here. And still the same base, right? So again, since you have to normalize back the results, so here, because of this carries which were happening during the addition, right? You arrive to a non-normalized number right now. So you have to, again, normalize it. And so you will represent it as 1.0015 to the 10 to the power 2, right? However, imagine that we have a hardware which can only keep 4 decimal digits, right? This is where we're running out of digits in the fraction, right? And in binary and in decimal, it works the same. So this we have, like in this specific case, we have 2 choices. We can either drop this 5, saying that we can only represent those 4 digits, or we can do a rounding, right? And this is the rules of rounding tells us if this digit is 5 or greater, then we round to the next digit here, right? So this is what hardware is doing. And this is the result of this addition. So essentially 1.002 to the 10 to the power 2, right? So, but you got the point that you, first of all, like all the results are imprecise because you can quickly run out of bits in the fraction and an exponent. So an exponent here, we say, look, the hardware can still keep this exponent, so it's fine. So it's not an overflow, right? So we normally check for the result of over or underflow, but that's okay here in this example, but we still do the rounding and normalization again. And sometimes it can happen that, you know, imagine you are rounding and the result of your rounding denormalizes your number. And then you have to normalize again, right? Because if you say that, like imagine you had, instead of 1, you had 9 here, right? And maybe the number is like something 999, and then you're rounding, and then you get to the something like this, right? So you have to normalize again. Okay, this is clear. So the binary addition works exactly the same. So it's same idea. You have 2, for example, 4-digit binary numbers. Both are normalized, so 1 point something, and then 2 to the power of some exponent. Again, we aligning the powers, getting to the same power here. And so what is our original example was 2 to the -2 power. So then if we want to normalize to the 2 to the -1, we shift it, right? And so we do addition of those, we call them significance, right? So it's this the whole part. This is the result of this addition. Again, we are normalizing and checking for underflow, overflow, so it doesn't happen here, so the power changes. So we don't have to round anything. So this is our essentially our number. And if you again, if you convert it to a decimal number, that's the answer in decimal. So as you see, this addition, the hardware itself is becoming more complicated because there is a couple of steps involved here. So you align them, right? Then you add the significance, then you do normalization and checks for underflow or overflow, and maybe you do rounding and normalizing if necessary. So you can guess from even from these algorithms that it will not fit in one cycle. I mean, you can build a circuit which fits in one cycle, but then the length of your cycle essentially is growing, right? And everything else will be affected by it. Because remember what cycles are. Cycles are to make sure that every circuit in your large CPU essentially converges to a stable result by the end of the cycle, right? And if you say that this intermediate computation takes so much time because there is actual propagation delayed between the gates, then you have to make your cycle larger. And then everything what used to fit in a cycle, like normal addition now, instead of like fitting in like 0.5 nanoseconds, might be sitting there and waiting for like 2.5 nanoseconds, right? And your machine, like everything, all the additions will be also done in, instead of being done in 0.5 nanoseconds, will be done in 2.5 nanoseconds, right? So it's like slowed you down by a lot. So that's why it doesn't make sense to essentially try to fit this floating point addition in one cycle, but instead like split it in multiple cycles. And then if you have multiple floating point numbers, you can just pipeline them and do this addition in a pipeline manner. We'll take a look at pipelines, so you will understand better what it works, how it works, right? That's roughly these steps. So essentially, again, if you roughly split it, and this is your representation in memory with exponents, which you first like figure out the difference, do this shift, then do the shift for the fractions, right? So then do the addition of the fractions and start doing normalization, rounding. That's your logic. And again, I'm not asking you to understand it, but if we in class we will later understand the logic for integers. For floating points, if you stir this for long enough, you will understand what's going on, right? But it's exactly, it's a hardware representation of this algorithm, right? Okay, so what can go wrong here? As I was saying, with all this shifting and addition, right? So you can actually, if you only have like 23 bits in the fraction, so we had 8 for the exponent, 1 as a sign bit, right? So we have only 23 bits for the fraction. So you can, in those intermediate computations, right? So you can easily run out of those 23 bits. So typically what the hardware is doing internally, it actually has additional bits to make sure that when you doing this intermediate addition subtractions, you actually can keep intermediate results around without just throwing them away and forgetting about them. And only when you essentially doing normalization at this point, you will cut the number and make sure that it fits back into the 23 bits of fraction. Okay.
Will it also be?
It will. And to be honest, I don't really know what I don't know the standard, and I don't know what happens if you're adding a number to infinity. So I would assume that logically the answer should be infinity as well, right? What happens if you're adding negative and positive infinity? Is it 0 or is it something else? That's a little tricky at this point, right? Yes, it depends on your mathematical domain again. Usually it's not 0, but I don't know the standard. So, and it's nice. It would be nice to check. Unfortunately, this simulator, which we're using for our homeworks, which is STEM, right? It will not. I don't think they faithfully implement all the exceptions. That's what they explain on the web page. They say that they like approximate. They do a fair amount of those floating point operations correctly, but they might not be faithfully simulating the hardware. So I don't really know the answer. And so we really need to either read the standard, which I don't know, or get a real MIPS hardware, which might or might not implement the standard, right? And try. So multiplication is relatively, again, simple. So again, follows the same rules. So, but you don't have to do, you don't have to normalize or align the exponents because of what? Because do you remember how it works? If you have 10 to the power 10, 10 to the power -5, exponents essentially follow the rules of addition, right? Because it's roughly speaking, if you have 10 to the power 1 multiplied to the 10 to the power 1, if it's same as 100, or 10 to the power 2, right? So exponents can be just essentially added, right? And then you simply have to multiply the significance and just put the this point correctly, right? So if you do this multiplication, obviously you have to account for where this thing goes, and so your result produces a 10 to the power 5 in this example, right? And you have to remember it, and then you again normalize and check for the overflow and underflow. And again, if the rounding sometimes breaks your normalization, you again normalize again, right? And then you, okay, one specific example, what do you do with the sign, right? And so the sign is actually determined from the sign of the operand. So essentially you multiply them as two positive numbers, but then just keep track of the sign and then produce the sign accordingly. Why do we normalize after what?
does it say subtract bias from the sound? But would it always have R?
That's a good point. I forgot to explain. So imagine, let's go here for a sec. Just wanted to get to the real, to how we represent the bias. So let me clear everything on this side. So this is what you keep there, right? So if you actually keep a number, if your power is actually +5, right? What you will be keeping there is a shifted number, right? So 5 minus 127, right? And if you, for example, adding them, right? So imagine you adding, again, just for the sake of it, 5 and 6, right? So the second is also 6 minus 127, right? And you adding them. So your goal would be to essentially arrive to something what is 11 minus 127. But if you blindly follow those rules, you will get this one by 2. That's why you have to kind of account for that. And I mean, if you're adding just 2 numbers, then you can just subtract the bias again, right? But if you understand that you either can like get rid of this bias here and then like introduce it back here, or just like keep the track of bias and then subtract it one more time. So to prevent accumulation of bias, right? Because it shifts you further away. So, but good point, and I missed it actually, I forgot. Okay, so multiplication is relatively easy, right? So slightly easier than addition. And finally, let's take a look at the instructions which the MIPS machine provides to work with floating point numbers. So first of all, it used to be that this floating point arithmetic, it was so complicated back in the days that it wasn't fitting on the main CPU, just in terms of gates. So there was just a limited budget. Remember, I brought you this the buffer in the second lecture. And back in the days, the resolution of how you were able to print the gates was low, right? And you could only fit so many gates, right? And if you want to implement the logic of your pipeline, it takes you, let's assume, like 1 million gates, and and a floating point logic might take another million. It just wasn't fitting on the same piece of silicon. So they put it as a separate device, actually a separate unit of silicon, which was communicating with a bus, right? So that unit was called coprocessor, right? And you could probably have multiple. It's somewhat similar to how we treat the graphical programmable GPU devices, right? Today, so there are separate physical units. Some of them fit on the silicon, right? So you can buy, my machine, for example, has a built-in graphical coprocessor, right? Which fits in the same unit of silicon. But if you buy like a beefy NVIDIA thing, it's just a separate thing which sits on a bus, right? So it was the same story back then. And that's why it changed the instruction set a little bit, right? So first of all, the operations were performed by that other unit, right? So that other unit was providing 32 single precision floating point registers, right? So starting from F0 going to F31. If you would like to represent double precision numbers, those registers were paired. So essentially F1 was paired with F0 to represent a single double precision numbers, right? And so essentially, if you wanted to use an instruction which operates on a double precision number, you would use something like, you would provide an argument to the instruction would use F0 as an operand, right? But implicitly it assumes that F1 is actually is loaded with the second half of that number, right? So it was providing this load and store instructions, and this C stands for coprocessor. So it's like load word coprocessor 1, load double coprocessor 1, store and store double coprocessor 1, right? So something like, for example, load double into the register F0 starting from this address on the stack, right? So all the addition, subtraction, in divisions, they would have this S or D suffix. So essentially add a single, subtract a single precision number. So this is an example, add two floating point numbers, which are inside F1 and F6, place result inside F0, right? If you would like to work with double precision arithmetic, then you say, again, remember F4 paired with F5, F6 paired with F7, and place the result in N4 into F4, which is paired with F5 again, right? Right, so it's an operation on a double precision floating point value. The comparisons, they work a little bit different. Remember, as I said, in our normal branch then equal instruction, if you have two arguments, for example, S0 equals to S1, then jump to some label, right? But since this floating point comparisons are done by two different units, so if you have this CPU and you have a coprocessor here, then this guy operates on floating point numbers. It can compare them, say which one is larger, which one is smaller, and later kind of send a signal back here, right? So that's why this comparison instructions is split into a separate instruction. So it's comparison where you can put, instead of this XX, you can put like equal, greater, and such like stuff like that, right? And you can compare singles, so double precision values. So for example, C less than and single precision, right? It takes two arguments like here, and this will be done by the coprocessor, and then the output of this operation will be sent to the main CPU, and then your branch instruction will simply take the target, the label. It will just essentially read the result of this comparison from a hidden CPU register, which we don't even provide here as an argument, but simply just say, okay, if it's true, then it will jump. If not, then it will not jump.
Doesn't matter if you have 1 or 2 X's from C.X.X.S.
No, access here means that instead of it's a placeholder which will contain one of those two letters, equal, less than, less, LE. What is LE? Less than equal. Okay. Yeah, you're right. Less than, less or equal, right? And so it just that instead of like enumerating all possibilities, that's just a notation which says XX will be one of those two letters. That's the form of the instruction the instruction will take. But that's the most important difference. So one is pairing of register for double precision, and second is that the branch instruction doesn't take register arguments because the operation is performed on a different hardware unit, right? Right now, obviously, the CPUs have a huge transistor budget, so it's super trivial to have everything together, but the instruction set has not been changed.
Are the floating point registers, do they exist on coprocessors?
Right. And all this, like, just because, like, all this logic for this, like, floating point additions and stuff, which I was showing briefly, it actually is implemented by the coprocessor. And this floating pointer registers exist there as well. So when you do a load into a register, it will go exactly there.
You can't make some, you can't use them on our processor. Like you could
An integer to a float. Right, but there is an operation which allows you to, I think, load a floating point register from an integer, if I understand correctly.
Yeah.
I'm pretty sure there will be one. And then it will be compared here. But yeah, so this CPU doesn't know how to work with floats, just because the logic is so complicated with all this alignments and shifts and stuff that it was implemented as a separate unit. So this is example from x86. This unit was called 8087, floating point coprocessor. That's not important, but what I wanted to show here is a simple piece of code which essentially converts from Fahrenheit to Celsius, and this is the conversion formula. So you take the number in Fahrenheit, subtract 32, and multiply by 5 nines, right? That's like physics. And so you can assume here that this one is in Again, I don't know the calling convention, but let's assume that the result is inside F12 and the argument is inside F12 and the result of the computation is inside F0, right? So when you compile this function, you will see something like that. So load word into coprocessor 1. So which essentially uses the address relative to this static global portion of your program, right? So this is where your constant 32 will be sitting, or no, it's actually constant 5, right? So that's an offset within the data section, right? Remember this. So you load it inside the register F16, then you load the constant which represent 9. Again, that's the offset within the data section. This is your data. And this GP points here, then it's just an offset where you have 5 and an offset where you have 9. Those are generated by the compiler, right? Because compiler has to generate correct representations of those floating point numbers in memory and just place them there. Then you do the division, 5 by 9, right? Place it into register F16. Another difference from a integer division. Remember, integer division was taking 2 arguments and placing the results into 2 registers, high and low, right? So here it's not done because there is just enough hardware capacity to essentially like divide 2 registers, and there is no quotients here. There is no and remainders. It's always the real number. So everything is done by hardware. So you don't have to keep them separately, right? So it doesn't make sense to waste. First, doesn't make sense to limit to just a pair of registers, high and low, right? Because if you have 32 floating point registers, the results can be kept again back in the same floating point registers without like constantly moving back and forth between high and low, right? Here you load the constant 32 into a floating point register, do the subtraction, result is inside F18, and finally you do a multiplication of this one by this one, right? And you can imagine that the compiler would do this division itself and already have a constant ready for you, but just for simplicity, in this example, it wasn't done. And since we want to put the result back into the register F0, that's where we are, and jump through a register to the returning result to the column, right? So actually, this is what I wanted to show today. And this is probably our just one lecture on floating points. There will be probably some kind of a homework on addition, subtractions, and floating points next week. And next week we actually will start building the CPUs, essentially digital logic and building the pipeline. Okay, thank you. See you next time.
So you specifically said that we need to we don't know like how to track
Yeah.
Yeah, when we're doing this interactive assignment, I think you can watch a lecture to take a look at the example.